And really, I'm going to go kind of maybe nerd out or geek out on you a little bit, but I just think it's kind of interesting, when we think about our waste activated sludge systems and how we think they've been around or that it's been around forever. And really, it's just past its 100th birthday. And does anybody know why is it called activated sludge?
What you want to do.
Aspect of it. Somebody put air to it for the first time and it did something.
Yeah, perfect. Carl's heard this spiel before, I think. So what they first found when they basically started back in the day, you would maybe add air. You take your wastewater, add air to like an aeration basin like you have now, and it'd go to a clarifier, and then it would just go to the effluent. That clarifier sludge was just removed and just taken away as like a waste product. And they would get BOD removal as part of that. They wouldn't get a lot. They wouldn't necessarily get the BOD removal levels that you see today. But what somebody did was they started recycling the bacteria. So they started putting a RAS pump on that clarifier. And what they noticed was that they got better performance out of the system. And they didn't know why they got better performance. And so they called it activated. They basically just said, well, we're activating our sludge. That's kind of where it came from. It's as basic as that. There was an argument in the scientific community whether it was chemical or biological, because they didn't really know at that time what was doing it. I think we now know that it's mostly biological. Yes, there's some chemical things going on, but it's mostly biological reactions. By recycling the sludge, we're giving it more time in the system, and we're giving it more time to grow. So that's where the term activated sludge comes from. It's because it's active. It's doing something. We don't know what, but it's doing something. And now we just know more about what's going on, what bugs are there, and we know more about how to control it now. So when we think about SRT, this is kind of what the equation looks like when we start defining it. It is as Carl said, the aerobic, well, it's really the solids retention time. And a lot of times, most of the time, we're referring to it as the aerobic SRT, the aerobic part of our aeration basins. And we'll get into why we're specifically referring to it as the aerobic part. But what it really comes down to is what we're measuring is the mass of our inventory. So this is the previous session where we looked at yield or production of sludge. So how much inventory is in our system versus how much of it are we wasting out? And this is our control variable. So we're able to control this variable here, our WAS. And the SRT is something that we set. This is our target. We want to target an SRT, and we'll get into how do we develop that target. But if we start breaking down these high-level terms of inventory, so inventory is just how much biomass you have in the system. What's the inventory of your grocery store? What's the inventory that you have available to you? And that's really coming down to what's your mixed liquor times your aeration basin volume to get that mass of pounds in the system. And that's that mass of pounds is really bugs. What bugs do you have available to do work for you, and what work do you need done? And then that's really kind of that variable is largely controlled by what kind of food you have coming in and a bit of what SRT target you're picking. And really what's controlling that then is that SRT target, and when you pick that target, the variable you really have to control is this QWAS target. We're able to control our wasting rate. Generally, a plant has a fairly consistent RAS concentration. It may change a bit, but in general, each plant has a kind of a specific RAS concentration that they typically see. And the variable you're controlling is this QWAS, which is controlling that wasting pounds per day. So whether you're setting a pounds per day you want to waste, so somebody's doing calculations and they say we need to waste 10,000 pounds, and then you back into it, you ultimately get to how much flow do we need to waste out of our system. on any of that so far? So Miguel asked, controlling your F to M ratio. Is the Q WAS your WAS flow? Yeah, so that's a good point. I guess I'm using engineering terms. Q is a term we use for flow. I shouldn't do that anymore. So Q is often a term we substitute as a variable for flow, and so that is your WAS flow, Miguel. And kind of similar to a digester, we do have F to M's in our activated sludge systems and our secondary treatment systems. What I encourage people to do is get your wasting targets from your SRT. So first set an SRT in your system. It's a little different than a digester because we'll show you why it's different than a digester. But let's say we set a 10-day SRT. So then we can start having our system, we can start picking our Q, WAS, our flow. We can start basically letting the system come to steady state. And then when we do our F to M's, we can do our food divided by our mass in our system. So F to M is food. So food is BOD divided by mass, which in this case is like MLVSS, like our VSS in our system. And so what I would encourage is you first get your SRT to a range that's acceptable, and we'll talk about what is an acceptable SRT range. So let's say that's 10 days. Then you can start looking at F to M's. And maybe what you find is that, hey, if I operate at a 9-day SRT, that's still within my acceptable SRT range, but I get a better F to M. And with better F to M, sometimes I get better settlability, I get better performance. And so I would use F to M as kind of a secondary measurement, a secondary guide. So kind of looking at this from a in a process flow diagram in our aeration basins, when we talk about that sludge retention time, what we're really talking about here is this kind of retention within the system, right? So we're recirculating around in a system. And so what that allows us to do is decouple the liquid flow from the sludge flow. So if I flip to this next slide, we're going to have the same system, and we're going to use, I think I saw more Denton Creek people on today. So Colby, I don't know if you can type. Carl might have to do it for you, I guess. So we're going to calculate the HRT of AB3. So to calculate HRT, we need the liquid volume of AB3. What's the liquid volume of AB3?
Good question. I think it's rated for.
It's like 1 point something. Let's call it 1.4, Carl. How does that sound? 1.4 million gallons?
Yeah.
Like 1.4 million gallons. And you're usually sending 6 NGD to it?
Give or take, yeah.
Let's call it 6. So if we're looking at calculating our HRT of our system, we're taking our volume, so 1 million gallons, divided by 1 million gallons per day, and that'll give us days. So can anybody, besides Carl, can somebody else do the calculation on the phone and answer it? I want it in hours, not days. I'm looking at the chat, so if you want to put your answer in the chat, I'll see it too. All right, does anybody have the answer in days? How about that? There we go. We got Miguel said 5.5 hours. That's right. So if we were to do the previous calculation to kind of walk everybody through what Miguel did, if we did the first part up here, we'd get 0.233 days. So if we have days, and we want to convert it to hours, I find it best just to break it down into like a like kind of a fraction multiplication, so you can cancel your units. So if we're trying to get days into hours, we need to have hours on top. So we know that 24 hours is equal to 1 day, and that way our days, the units cancel out. And then that's where you end up with 0.23 times 24, and that's where you get your 5.5 hours. Oops. 5.5 hours. And so the point of doing that, though, is to kind of show you the example of our HRT, so our water flow going straight through the plant, is about 5.5 hours for this aeration basin. But the SRT of this system, Carl, what's your SRT of AB3?
Right now, yeah, Jacoby said 4.6.
4.6. So yeah, so that's where you get this decoupling. Like you're separating the two. HRT does not equal SRT. Like they don't equal. Miguel, how does that compare to a digester? Do HRT and SRT equal in a digester? So if I were to draw a digester similar to this, so a digester, we can call it kind of a secondary treatment system if we want. We send solids to it, and we send solids from it. There's no clarifier. So to have a 15-day, and Miguel, you're right, HRT equals SRT in a digester. So if I have a 15-day SRT requirement in a digester, I need a digester that has 15 days of volume. So that's where you get very large digesters. But when we have a clarifier in our secondary treatment system, this is what allows us to separate the solids and not have a very large aeration basin. So that's kind of the point of all the RAS flows and recirculating it, is to reduce the size needed for our systems to get to that 4.6 or 10-day SRT. All right, so we have a problem here. I am going to give what I want you to do, and then I'm going to give people some time to solve it. So we're going to calculate wasting with SRT. So going through what we want to do here, we want to calculate our current biomass in the system. So we want to calculate how much mixed liquor or inventory do we have. Then we're going to calculate the mass-based waste based on a target SRT. And lastly, I want to get to calculate the volume or the gallons to waste out of our system. So to do this, the first step we're going to do is this, where we're going to calculate our biomass inventory. Then we're going to take our inventory and we're going to use an SRT target to get a mass to waste. So how many pounds per day are we going to waste? And then lastly, we're going to use an equation to get how much volume does that equate to when I'm wasting. So here's the problem statement. I'm not going to give you any of the equations. I'm not going to kind of give you any intermediate answers. I'm going to give you about three minutes here to see if anybody can solve all the way to the bottom, and then I'll start giving equations and we'll solve it step by step. So I want everybody to try. I'll give you one more look at the equations. Remember, you're looking for your inventory, then your pounds per day, and then your gallons. And I would say for now, don't put your answers in the chat. I want people to try to solve them. I want people to try to solve it. I'll wait for 3 minutes and then I'll ask for answers. We have all the way to the bottom answer. So I'm looking for gallons per day. Does anybody have that? All right, I don't hear any takers, so no, we don't have anybody at the bottom. Wait, Miguel said he has. What are the units on your answer, Miguel? So Miguel's answer down here is 0.0917. What are the units on that?
I'm sure this is wrong too. I couldn't remember your calculation for number 3, but I've got 10,991 gallons as far as volume goes.
Yeah, and Miguel, you're in MGD. So Carl's in gallons per day. So to put Miguel's answer in MGD, Miguel's about what is that? I think he's 9,170 or something like that. Miguel, that's what yours is. So you and Carl are close. to gathering answers at least. Let's start at the beginning then, and let's see if the answer is one of those or is it something else. So our biomass of the current system, so we have 2.75 is our volume times 3,000 times 8.34. And that's what Miguel put in the chat. And Miguel had 68,805, and that's pounds. So that's our inventory. That's how many pounds we have in our system. Does anybody, as we keep going through, what is this 8.34 doing?
It's your weight of a gallon of water.
Yeah, that 8.34 is our conversion to pound, weight of gallon of water, conversion to pounds. That's what it's doing there. If we put if we put something in terms of milligrams per liter times million gallons or MGD, and you multiply by 8.34, that gets you pounds. And whether you're using the pounds versus pounds per day is whether you're using MGD or million gallons. So it's whether you're doing a volume or a flow rate. All right, I'm going to go to a different slide because this slide's getting too busy. Equations. So we're gonna do our mass to waste. So we basically set this 68,805 as that's our biomass inventory. We set our SRT target as 10 days. So that goes down here. So then this answer gets us 6,088. We'll just round it to 1. And that is pounds per day. And that's how much we have to waste today. That's our mass we need to waste. And so the variable we have left is what is our TSS of our mixed liquor, or our wasting, our RAS, our WAS. And so that to do that, that's where we're bringing this back in here, where we have our pounds per day. So we're reversing that equation and we're dividing it by 9,000 times 8.34. And that should end up with this 0.0917, I think. Yeah, so I got 0.0917, and because we're using that same equation, that's an MGD. And that, to get from MGD to gallons per day, you just multiply by 10 to the 6th. And that's where we get that 9,000. Carl, I'm wondering if you rounded somewhere. Like you rounded off a number to 7,000 or something like that. I know there's a lot of, my handwriting on here is terrible, and there's a lot of text on here. Any questions on what we went through there? A lot of it is unit conversions. If you can get through unit conversions, it helps a lot. Miguel, I'll make sure you get a thumbs up on your year-end review. I can't guarantee any bonuses or raises, though. All right, I'll keep going here. So when we do have the slides out there, and if you're going online to see them, the answers will be in here. We have them kind of stepped through in a very poor fashion. Jeez. All right, so now we're getting into, so we figured out how to calculate wasting. Right, so we've gotten that far. We can figure out how now we know we can do yield, we can take our BOD coming into our system. We can estimate how many pounds we'll yield. From those pounds we yield, we can estimate our mixed liquor concentration. And now from that mixed liquor concentration and inventory, we can start to use an SRT target to develop a wasting target. So now we have we're starting to build our toolbox here of equations and knowledge of how to start building these and how they all relate to each other. And so when we think about it, what we can start understanding now is when we have a change to influent loading, our biomass is going to respond. So if our BOD goes up, our mixed liquor is going to go up. If our mixed liquor goes up, that may mean if you don't change your wasting, that may mean your SRT is going to go up as well. If you adjust your wasting, that'll increase your WAS fraction to maintain the same SRT. And so it's a matter of each day you're doing this calculation and you're creating a habit. You're forming habits so that you're able to manage the solids in your system as they continue to change. And these habits should really start to be formed on a daily basis. You know, it may seem like an intimidating thing to do each day, but once you have a system kind of at steady state, it's minor adjustments every day. You shouldn't have any drastic adjustments each day. It should be minor adjustments. And what you're doing and what I would encourage each plant to do and think about is, you know, you want, maybe it's by 8 a.m. you have your mixed liquor from the previous day or the previous night. You have your mixed liquor from that day. You have your SRT calculated, and you say, well, my SRT target for today is 7 days. And then you do a calculation quick and you figure out how many pounds and gallons you need to waste from the system. I assume you kind of coordinate or communicate that with your operators about your target wasting for the day. And then you go about and do other things with your day. So like this should be something that occurs every day, or you should be looking at it and making sure that you're kind of setting those targets, but then you can generally go about the rest of the part of your day. What are some key samples that you'd want to do these calculations every day? What are some samples? So if we go back to these equations, what are some of the things that you need from the field? What are we relying on operators to go grab samples of? Yeah, so Colby said the mixed liquor. So that's one of them. And the RAS mixed liquor. That's the second one. Those are the main points. You know, when we're looking at our volume to waste, we're relying on flow meters. Hopefully those flow meters are good. But in general, when we're talking about these mixed liquor and RAS TSS numbers, these are all of you on this call, or most of you on this call, are grabbing those samples and you're testing those mixed liquors, and you're testing that mixed liquor and that RAS TSS. So it's important, if you get a number that seems wrong, that you just maybe ask yourself, does that seem right? And should I go grab another one? Or maybe I ignore that one and I take the previous shift's number because my number was double their number. So that's why these samples are important, because they're playing into your calculation and understanding what the mass in your system is, because you don't want to overwaste and underwaste your system. Lastly, KPI. So Miguel asked what KPI was. Sorry for using these terms. KPI is key performance indicator. So if I have KPIs for my plant, one of my KPIs, a KPI could be that I want, if Carl says we need to waste 91,000 gallons today, and he tells Colby that's a KPI for Colby. Colby needs to try to achieve that KPI today. It's like a goal, fancy word for goal. So what drives our SRT selection? So now that we kind of know how to calculate wasting, how do we get that 10-day number? How do we get that 7-day number? How do we get 4.6? What is driving that SRT selection? So our SRT selection is really driven by what are we trying to do in our system? So if we look at what we're trying to do in our system, are we trying to remove BOD? So we're trying to move BOD in our systems. That's taken place by heterotrophic organisms. So you don't have to necessarily get caught up on the word, what heterotrophic is or how to spell it or how to say it. Heterotrophic organisms are kind of the workhorses of our aeration basins. If you were to look under the microscope, over 90% of what you're looking at is a heterotrophic organism, probably more than that. So most of the bugs you see under a microscope are heterotrophs. They're doing a lot of our BOD removal, and there's lots of them, like millions of them. If we were to think about how would I describe heterotrophs to like the larger world, I would describe heterotrophs as all the animals on Earth. And all the animals on Earth, there's a bunch of different types of animals that can eat our BOD. So there's a huge variety of animals that can break down BOD. And so from that standpoint, it's BOD removal is typically very robust. You usually don't have issues with BOD removal. That's one of the things that is usually pretty straightforward. If you're settling your solids, you're usually removing your soluble BOD. These heterotrophic organisms, they're resilient and they grow fast. And there's so many of them that if one doesn't grow, another one will grow. A different type will grow. The next thing the only plant on the call that has to worry about it is phosphorus removal. And what we call those phosphorus accumulating organisms. So they're technically a heterotroph, but they're a specific type of heterotroph that we grow and select within systems that need phosphorus removal. And we typically shorthand call them PAOs. The next one is nitrogen removal. So that's nitrification, and every plant has nitrification requirements. So when I'm talking about nitrogen removal, I'm talking about removal of ammonium. And to do this, we have what we call nitrifiers in our system. And these nitrifiers are broken down into two different main bacteria. We have what we call ammonium oxidizing bacteria, or AOB. They take NH4 to NO2. So they're taking ammonium to nitrite, and then they pass that nitrite off to the NOB, who take NO2 to nitrate. And that's what leaves your plant. So within our plant, we're taking ammonium and we're basically just converting it to nitrate, which leaves the plant. We need bugs to basically work together and handing things off from one to the other. And when I'm having conversations or phone calls with people and they're talking through some issues at their plant, and one of the things that I may ask you is, have you taken an ammonium sample? We'll get to why. And the second thing I might ask is, do you have any nitrite kits? And the reason I might ask about nitrite kits is because one of the first things that starts to pop up is the handoff between these two bugs becomes disrupted. And so if you start seeing nitrite, that means you're having incomplete nitrification. Something about these bugs are upset. And we'll get into kind of why we're looking at these versus BOD. So when I look at BOD removal, again, we're talking about those heterotrophic organisms. And when we talk about growth rates, that's what this is. This doubling time is growth rate. So for one bacteria to make a second bacteria, heterotrophs take 3 to 10 hours to double. So to go from 1 to 2, they can do it as quickly as 3 hours. And if you remember, when we did the HRT calculation in our aeration basin, our aeration basin had a 5.5 hour HRT. So now you can kind of start to see, when they first had systems back in the day where they just aerated it, They were growing heterotrophs. They just weren't growing that many. The HRT might not have been quite long enough. It wasn't getting as high of removals as we do today, but they were still getting removals. But as soon as they started recycling it, so they went from just going straight through once to recycling it, they started seeing even more removals because you're giving them longer to grow. So you're getting your inventory is going up. Now as we keep going, so those are relatively fast growers. Our PAOs, their doubling time is 12 to 24 hours. So they're a little bit slower growing, but they still have a pretty quick doubling time. And the worst doubling time is the AOB and NOB, which take 1 to 2 days to double. So if we're talking about 1 to 2 days to double, that's the slowest growth rate out of all of these. So when we think about our slowest growth rate, well, if we want to nitrify, which we do, we want to nitrify, we want to have these bugs in our system, we need to give them at least the amount of time to double. Like we need to have one bug be able to create another bug. Otherwise, if they don't have enough time to create another bug, you're gonna wash that bug out and you won't have it left. So you need to give it enough time to double, and that's what we call washout. So washout SRT is this doubling time. So if we're operating at below washout, it means that our bugs are getting wasted faster than they can produce. So getting back to why if you're going through a process upset, why would I ask about ammonium, effluent ammonium, or effluent nitrite? It's because I want to know, is it SRT related? And the first indicator that something is SRT related is ammonium, because these guys grow the slowest, meaning that if you're trimming your SRT too low, you're going to start washing them out. And as you wash them out, you might start to see your ammonium go up, or you might start to see your nitrite go up. So if you wash out NOB a little bit faster than AOB. And the other reason I ask about these ones as well is these bugs are the slowest growers. They're also the most sensitive in the system. So if you have some kind of inhibition or some kind of spike load, they're the most sensitive to all of it. And they're usually the ones to kind of start not functioning the first. They're kind of the snowflakes of our activated sludge system. So now if we talk about washout, so our washout SRT, here what you're seeing is a graph that shows SRT curves versus temperature. So not only do we have to think about our bugs, we got to think about our temperature. And apologies for making it in Celsius, but over here you can see it in Fahrenheit. This is a typical Texas plant. So this is 17C, so about 65 degrees is your wastewater temperature in the winter. And in the summer, it gets up to like 86 degrees. It's pretty warm in the summer. And so as it gets colder, things slow down. The growth happens slower. A lot of times, so this is your washout. So you can kind of see if I had a plant that was, maybe I'll give you an Iowa plant. An Iowa plant might go from summer of here to winter way back here. So that's a 3 to 4 day change, where really the difference between a Texas plant is only about a day and a half change between winter and summer. It's rare you see Texas plants shift between SRTs summer to winter. Up north, if you ever move up north, and I'm talking like north of Missouri, north of Colorado even, you will see plants shift between winter and summer SRTs because the difference is so large, it has an impact on their mixed liquor. So we'll get into that impact here, but this is essentially saying this is the washout SRT. So this is what the SRT you need to operate at just to be washout. So there's no safety factor on this necessarily. And I would say even getting down to this like low temperature, you've got to be pretty cold to hit that low temperature. And this is, I think, Carl, you're still on. This is where I was asking you and Jonathan if you had temperature data of your wastewater, your aeration basins. You guys might get this cold when it turns to, if you guys remember, like when you had a week of freezing cold temperatures, like with 7 days of below zero or below freezing, you might have hit this temperature. Wastewater generally stays pretty warm. You're probably more operating in here.
Eric, you got a question in the chat from Miguel.
Oh, sorry. I need to bring that up. Yeah, so Miguel asked, is the change in the curve here because bugs become slower and when it gets colder? And the answer is yes. And to kind of, so Miguel is working at cruise on the solid side. So Miguel operates a digester. Miguel's digester operates way up here at 35°C. The reason we heat digesters, Miguel, is because your bugs in the digesters grow so darn slow that we don't have time to wait for them to grow back in here. Your curve for methanogens is going to be like way up here. So methanogens are where you're trying to grow in a digester. So each bug has its own curve. I could even show a curve for heterotrophs. So a curve for heterotrophs is going to be something like way down here. So all of these are just related to temperature and growth rates. So now let's go through our SRT. So I think we have Denton Creek on the phone. So we're going to talk about safety factors. So what we normally do, if these are our washout SRTs, normally, if I'm an engineer, I'm designing your system at a 2 safety factor. So I'm taking your minimum washout SRT and I'm putting a 2 times safety factor on it. So my winter now becomes 6 days, and that's what you can operate at in the winter. My summer, I'll round up and we'll just say 3 days. My summer, when it's warm out, I can get down to 3 days and operate with a 2 safety factor. And generally we call that, that's safe enough. There are plants that maybe operate that need a higher safety factor. And those are very specific use cases. And when I say a plant might need a 2 safety factor, I'm talking about like ski resorts. Or sorry, they might need like a 5 safety factor. Ski resorts are crazy because they go from no load to huge loads over the course of a day. But let's calculate the safety factors for our plants. We're going to go ahead and assume that our washout SRT right now, that's what this W is I don't know. Let's go up here. Let's look at, let's say that it's probably 24 degrees outside right now. I don't know. Or not, it's not outside, sorry. This is water temperature. So let's say it's 24 degrees. So our washout, let's call our washout 2 days. So our minimum right now is 2 days. So we have Denton Creek on. I'm sorry, who else was, let me look at my phone. Guess I think we just have Denton Creek. So Colby, I think you said your SRT was 4.6 days. Sorry, I'm trying to get to my attendees. If there's any other plans on, please speak up or put something in the chat. Miguel, we'll get to yours. So if I'm trying to calculate my safety factor, so Denton Creek, they're operating at a 4.6 day SRT. And then if our minimum SRT is 2 days, that puts your safety factor right now at 2.3. So the Denton Creek safety factor is at 2.3. I'll give Cruise crews, they typically operate around 12 days. If I divide that by 2, they have a safety factor of 6 on their system. And then Miguel, I'll give you one for your digester. So Miguel, the cruise digesters, their washout SRT is about it's about 8 days. Your actual SRT, I don't know, Miguel, I'll put you on the spot. Do you know the SRT of your digester? Yeah, Miguel, you said 16. I think that's about right. So you're at about a 2 SRT. Digesters will take down to a lower safety factor than 2, mainly because the load doesn't change very fast in a digester. So like your digester, Miguel, from a design standpoint, is designed to go down to 12. And so if you're 8 day, so it's usually about, what is that, a 1.5. So you can kind of see a digester will take the safety factor down a little bit lower because there's less variability in digester feed. Digester feed, you're mainly taking WAS, which you can kind of predict day to day, and you're taking primary sludge, which is maybe a little bit less predictable, but we usually will trim the safety factor on on a digester compared to a plant where we can't necessarily control slug loads. So now, what does the safety factor mean? So this will be our last few slides here. So when we're getting into our safety factor, and this is a safety factor for anything, but we're really focusing on nitrifiers because that's what we're worried about in the mainstream. If we're Miguel and we have a digester, we're focusing on methanogens. But the orange bar, or not, sorry, the yellow bar, this is mainly your washout. This is your washout SRT. So we can operate at washout. Like if we operate right at that washout, that means we're giving the bugs just enough time to produce one more. So we're wasting one, but that bug just had enough time to produce one more to replace itself. So it's a 1-for-1 kind of exchange. There is no extra time in there. If there's any inhibition, if there's extra load, there isn't anything extra to do it. So if today I'm treating, let's say today I'm going to give it a small number. I'm treating 5 pounds today. If I have 6 pounds come in tomorrow and I'm operating at washout, if my nitrifiers take 1 to 2 days to grow, it'll be tough for me to be able to accommodate extra load. And that's why we start talking about these safety factors, which is what's on the bottom, this SF. And we're starting to build extra inventory. So we're building that extra inventory, and that way, if we have something higher come in tomorrow, we have extra bugs there to do it. Eventually, this levels off though. So running a 100-day SRT, it doesn't just keep increasing and be beneficial. Eventually what happens is that you have so many bugs in your system that they're dying faster than they're growing. So it's really going to start to level off as you start increasing that safety factor higher and higher. There's only so much bang for your buck you can get by having a higher safety factor. Just because typically from a day to day, you can't carry an inventory if you don't have enough food to feed your inventory. So that's the kind of balancing act you're playing here. Any questions? Yeah, go ahead, Carl.
Yeah, real quick, just a good comparison. We can talk about when Denton Creek was taking on the crazy flows we had in quarter 2 with the rain events. We were down there close to that two-day safety factor, where what was critical there was the fact that we had, as the months went on, the loading got higher as far as BOD. Ammonia was still diluted as far as I&I, but the BOD was higher because of the settling out in the system. So it was difficult to to make do on daily process, right? And then you can look at the other side of it when you're talking about SRT and 20, 30 days. There's another plant with TRA that's had that on the other perspective of what that creates, right? So
Yep.
you've had both spectrums here in the last year of it being difficult on both ends.
Very extreme spectrums.
Yeah.
And to get to Carl's point, Carl dug into this safety factor this spring. Carl, you were somewhere in here. You maybe had a few days over in this one. But the advantage Carl had, and I'll call it an advantage, I don't know if there's any advantages, was Carl was mainly treating the same flow every day. The whole collection system was filled with water. And then, like he said, Carl's ammonium concentration was relatively consistent, right, Carl? Like it wasn't changing a lot day to day.
No, it was around the 20 parts, give or take, coming in. So we were able to step feed and push the plant harder, but the BOD started to peak his head up. And that's where it got, like when you show the comparison of the you had 5 pounds coming in and then you had 6 pounds coming in the day after, that's where it got hairy as far as control goes.
And that's kind of, I mean, I think there's been very extreme cases of both. And I think for the Denton Creek staff, I think that was like all of these slides are a very good learning opportunity of what you did and what you will continue to do for the next year to 2 years. You're really trying to, I'm not saying you're going to keep pushing your safety factor down lower and lower, but you're really trying to get in this range here, because what happens, let's see here, I thought I don't have a slide on it. So if I operate at a safety factor, to get to Carl's point and what Carl was balancing, I'm going to go down to here. What Carl was balancing, or Denton Creek, all the staff were balancing, was if I operate at a safety factor of 2, so if let's say my washout WSRT is 2 days, my safety factor in this case is 3, and then over here my same thing, but my safety factor is 2. What is my SRT that I'm operating at in both cases? So we'll call it case 1 and case 2. What's my SRT in this one over here? If my washout's 2, my safety factor is 3.
Yes, I'm not following you what you're asking there.
So if my minimum SRT is 2, but I'm operating with a 3 safety factor, that means I'm operating at a 6-day SRT. Sorry, okay. I'm being kind of confusing. And now if I take my case 2 and I'm operating at the same temperature, so 2 days, and I'm using a 2 safety factor, that means in this case I'm operating at a 4-day SRT. And so those 2 cases, and this is why we're getting into the safety factor and how the safety factor and SRT compare to capacity. Is my mixed liquor going to be the same in both of these?
More than likely, no.
Yeah, this one over here, maybe it's going to be 4,200, and this one over here, maybe it's going to be 3,500.
Yeah.
And this is where it comes down to your SRT determines your plant capacity, because this plays into your clarifier now and your blankets. So I really want to kind of drive home that point of for a short SRT plant like Denton Creek was doing, or a long SRT plant like 10 Mile, all of these decisions about what you're making for your SRT, that SRT matters because not just because Eric said it did. That SRT is what's driving your mixed liquor, and that mixed liquor is what's driving your clarifier performance and overall how much flow you can treat. All right, this is my last slide. Any questions? I know we're over. You know, sometimes, Carl, I wish people would just say, I'm doing it because Eric said it. But any last questions?